Hi there, nice to see you return to our discussion of how row updates are being processed by PostgresQL. So we have just seen how delete and insert and update are reflected in the plans, in the query plans of PostgreSQL. But we have not yet discussed how a plan operator like the update operator really affects the heap file storage of the target table of such an update. And that's exactly what we are going to talk about in the next few minutes. So how do row updates indeed alter the heap file, the table storage? And let's focus in this discussion on the update operator that we've already seen in the previous slides. It's representative of what happens for deletions, for example. Okay, so when we look closer, and we will do this in a minute, then we will find that the update operator really indeed does not update the affected rows in place. The old rows remain in place, and a new updated version of the row is being created. The original old one and the new one, the updated row, they coexist. All right. So we had one version of the row on our heap file page. Now we have two versions, the old and the new version. And the internal operation of the database makes sure, and we will also see how that works in a minute, that any user, any application that queries the ternary table, for example, of course sees only exact one version of any row at any time. Either it sees the old version or it sees the new version. Okay, different applications, different users may see different versions of the row at the same time. Okay, and that's quite a clever thing to do, and it serves the purpose of isolating the users, the applications, from the effects that they have on the database storage. So an update on the ternary table that I am performing might be completely uninteresting to you at this particular point yet. All right, so your operation, your program will not be disturbed by the updates that I'm performing on the ternary table. When time comes, so that every user, every application should see the new version, the newest updated version of the table, then the system can implement this. But until that time, every user has its own view of the ternary table. Either it's being unaffected by any updates, or if I'm the user who's performing the update, I, of course, can see the new updated state of the ternary table. And this is not implemented in terms of copying the entire table, the entire ternary table, so that I can have my copy and you can have your copy. But it's about maintaining copies of the affected updated row versions only. Okay. This will, of course, lead to heap file pages in which many versions of the same row might exist. I could have many updates that are affecting the same row. Each of these updates will create a new version of that row, leaving the old version in place. So in an update-heavy workload on a database system, in an update-heavy application, I might have many rows, many versions of the same row lying around in my heap file. And most of these versions at one point will be considered garbage because they're obsolete and really old and cannot be seen by any user or by any application anymore, as time has moved on, in a sense. So there's a separate process, and we've already seen that in passing in our videos on PostgreSQL. There's a separate process, the vacuum process, that we can also initiate in the PostgreSQL shell. A garbage collection process that will wander the heap file pages and collect all those row versions, old row versions that cannot be seen by any application or any user anymore. These are really considered obsolete and dead. They will be collected and removed by the vacuum process, and we will gain free space on our database pages again. But until vacuum runs, old versions coexist with the new versions, the updated versions of the rows. So on the heap files, how would that be represented? So we have, of course, the original version of our row. That would be the starting point of all of this. And if you recall, such a row has payload data, which is of minor interest now, and a header part. Okay, inside that header, there is a row ID stored. And we were wondering in an earlier video why would that be the case? Because we are fully aware on which page this particular row is being stored, and we are fully aware about the slot pointer, the line pointer, that the offset, in a sense, that is being used on the page to hold that row. So we were wondering, why is there the additional row ID, the CT ID field in the row header? And the answer to this is becoming vital and very important once it comes to updates. So if our row is stored on page 0 at line pointer at slot LP0 originally, then a new updated version might live on a different page at a different line pointer or slot offset. All right, that new version of the row, we are pointing with this CT ID field, or with this row ID field. So this is the original version of the row. Its newer version is found on P1 LP1. So at this particular row ID. When the original is not being updated yet, then we would just find the P0 LP0 here, and we would just refer back to ourselves. But this is not the case for this row anymore. It has a newer version and it lives at P1 LP1. This is the new version of the row. As you can see, the payload has changed. All right, this would be the state after the first update. A second update would create yet another copy of this row with a changed payload, and that new copy would live at a different page in general, at a different line pointer or slot offset. Okay, and the first version, the version of the row after the first update would then, of course, refer to that newest version after the second update. So what we get is a whole chain of row versions here, and the chain would end at that row that points to itself. So this would be the end of the chain. This particular little loop here, this would be the end of the chain, but the whole chain is the entire history of that row, and all of these row versions are present on the heap file pages of our database systems. Okay, so now we would need some logic that makes sure that any user or any application can really see the correct version, the unique one correct version of all the versions that are maintained in this chain here. So this is about row visibility. And this row visibility is implemented in terms of a rather simple time stamping logic. Okay, so each row is equipped in its row header, that's a field we have not discussed yet, with two timestamp fields, the xmin and xmax fields. Okay, so actually X should probably pronounce as transaction here. So the minimum and the maximum transaction value is recorded here in this in these fields xmin and xmax. They are timestamps. So in this particular example, the xmin has been set to timestamp 0. The xmax has been t0. This xmax value has been set to t1, and the semantics of this is that this particular version of the row, is visible between timestamps t0 and t1 exclusive. Okay, so the visibility of the row is restricted, and it's only valid within these two timestamps. And as you can imagine, different versions of the row will carry different timestamps. An updated version of the row will have a visibility timestamp with xmin t1 and xmax t2, which is a timestamp interval that is after this that lies after this particular timestamp interval and would thus represent a new version of the row. Okay, there's some convention there that says, hey, if this row has never been updated, if it's the still current row, then there is no restriction on its visibility. So it will be, this version has not been updated. It's the definite version of the row forever, forever. And then we would set the T1, the upper limit of the visibility interval, we would set that to infinity. But as you can see in the actual implementation, it would be set to 0 this particular timestamp. But this is a representation of infinite visibility of this row, which has not been updated yet. Okay, so every user and every application in the system is assigned a timestamp too. So hey, you user, you are currently querying and working with the system, and your current system assigned time is the timestamp t. Any application has such a timestamp too. And if t is my timestamp, then we would just check whether t falls between the xmin and xmax values of a particular row. And if it does, then that row will be visible to me. All other rows for which I cannot find this timestamp included in the T0, T1 range would be invisible to me. Okay, so that's how the row visibility is being implemented in terms of a timestamp, a system-generated timestamp that is assigned to the life range in a sense of the rows, but also to the applications. So these timestamps are not actually minutes or seconds measured by the system clock of your system or something, but they are virtual timestamps. In fact, they should be called transaction IDs. It's, for now, we can think about transaction IDs as a system-maintained global counter that is being advanced whenever some operation, some query or update operation is performed in the system. All right. So we will see that we can actually query and see the current assigned system timestamp. There's a built-in function in PostgresQL, the transaction ID current, which will yield that t value here. So when we are talking about t as a concept in the slides, then it's actually implemented by the current transaction ID in the system. This is our representation of time that will be advanced with operation by operation by operation. We will see that. Okay. So I think it's time to play with this and really see how this is working. I think this is rather insightful. So time to go over to the terminal again. And of course, we are talking about the ternary table. And just to make sure that my previous runs have not destroyed the table contents that I'm relying on, I'm recreating it here. So let's look at the current state of the table. If you recall, this table is being stored on 9 heap file pages. So what I'm doing here is I'm looking at the contents of the table, but only selecting those rows that actually live on the last heap file page. So it's every row whose row identifier is equal to 9,1 or is even greater, so has a greater slot number here, that's being output. All right, so let's see which rows are living on page 9 of the heap file. Oh, it's 37 rows. It's the tail contents of the ternary table, as you can see. All right, so these are the rows that we are currently looking at, and we will shortly we will do an update on a row on this particular page, an update on the row with a value equal to 982. So this will be the affected row. Okay, this will be the affected row. We will set its C value to -1. It's currently 2.99 something here. We will set it to -1, a sentinel value that we can easily spot. And let's take note that it's currently stored on page 9, okay, in the 19th line pointer slot, the 19th row slot here. So row ID 919 will be affected by our update in a few seconds. Okay. So let's first look at the contents of the real row header contents of the rows that are living on page 9. So let's do that. So this is what we are seeing here. No, this is what we are seeing. I'm sorry. So this is a view of the now relevant fields of the row header of the rows of page 9. Okay. We will of course find our row 919 here. So this is the row that is going to be affected in a minute. Okay. Currently it lives on page 9 at line pointer slot 19. So 19 is the line pointer slot LP. And so it's no wonder that its row ID is currently recorded as 919 here. This is actually the redundancy that we were talking about. Why would I record the 919 explicitly here if I know that I'm currently looking at rows at page 9 at line pointer 19? But as you can see, as you recall from our discussion, this will probably change. And it will probably at some point point to a newer version of the updated row. Currently, this is not an updated row, as you can also see regarding these two false values here. These two false values here indicate that this is not an updated row, and it has actually not been touched, not been updated yet. Okay. We can also see this when we are looking at the xmin and xmax values of this particular row. Okay, so these are the xmin and xmax values. All right, and for this row, the values indicates that this version of the row has been visible since timestamp 48391. Since transaction ID 48391 has been run on this system, this row is visible. And its visibility is unrestricted yet. You see that this is the representation of the infinite timestamp. The version of this row is visible until infinity. All right. It's probably the case that the insert operation that created this row had been assigned the timestamp or transaction ID 48391. It's actually the case for all of these rows. They have been created as siblings in time. All of them have been created at the same conceptual time stamp. Okay. So let's see whether we are currently allowed to see these rows. And the answer to that would be given by looking at the current timestamp or transaction ID. If that transaction ID is larger than this xmin value and smaller than the infinite value, which is trivially the case, then we would be able to see the versions of these rows in our current database operations. Let's check the current transaction ID, and it's 48393. 48393 is actually larger than these xmin values. Yes, we can see the versions of these rows. As expected, we see the 1000 rows in the ternary table. And as you can see, if I perform more database operations, for example, querying the current transaction ID again, you will see that it's a global counter that's automatically being advanced by the system. So let's do that again. And it's at 48394. Now, it's really a global counter, a transaction ID counter. It's not the number of seconds since something or some. It's a virtual timestamp. And of course, we can still see the versions of the rows above. Okay, so now let's finally perform the update. This is the real update that will actually alter the heap file contents of our ternary table. Let's do it. Okay, so one row has been affected because we had a rather selective filter predicate here that's on a key column, specified on a key column. So now let's check the ternary table again. Let's check the last page of the ternary table again. This row, as we know, lives on the last page. Something should have happened regarding the contents of the last page that we are looking at here. Okay. Okay, so the row with row ID 919, the original row with a value 982, is missing from the output here, as you can see. It's missing now, but this is actually probably being expected because this is the row that had been affected by the update. It's missing at this particular spot. Oh, okay. But of course, it's not gone. It's here at the very end of the heap file. It's the row with the A value 982. The update didn't affect the A value. It didn't affect the string value in column B, but it has set a new C value, which is now -1. Okay, so the updated row also lives on page 9. We see the row that SQL semantics led us to expect. Everything is fine. You see that the row appears to be stored out of order in a sense. So before the update, all of the rows were nicely stored in A order, but as you know, that's a true coincidence. Now that order is gone anyway, the new row is stored somewhere at the tail of the heap file, at the very end of the heap file. So regarding SQL semantics, the row is still there. Ternary still has 1000 rows, and one row, namely the row with A value 982, has been updated to yield a new C value. So everything as expected. So now let's look at the internals of the page at the row headers again. This is the same query as before, looking at the row headers of those rows living on page 9. Okay, so the 919 row has been the row with row ID 919, so living on page 9 at line pointer 19, that has been the affected row. And it's still there. It's still there. This is the contents. I'm sorry about that. This is the contents of the page 9. And at line pointer 919, we still have interesting contents here. It's still contents. All right, line pointer 19. Okay. There's still a row there, but it's an updated row. This row has been updated, as you can see using regarding the T flag here. This T flag indicates that this row has been updated. Let's talk about this HOT, this hot annotation in a minute. All right, so the row has been updated. Okay, its new version. This is the representation of the old version of the row. Its new version is found someplace else. It's found on the same page, but at a different slot, at slot 938 now. Okay, so old version of the row represented by this entry, new version of the row to be found at 938. All right, okay. This old version of the row is relevant for you if your operation timestamp, if your transaction ID lies between these two xmin and xmax values. You see that the visibility, the validity of the row is now being restricted. Every operation with a timestamp that is larger than this 48395 will see a different version of the row, not this version of the row. Okay, so let's scroll to 938. We are lucky the new version of the row lives on the same page. So that's not a given. That's the good case. That's the good case that we only have to load one file from disk to find all versions. In this case, the two versions of the row on the same page. It would be bad news if we would find different page number here. That would mean we had loaded page 9 only to find an old version of the row and then to be forwarded to another page that will hold the current or a newer version of the row. So that would be one page IO in vain, and that's actually bad news, as you know. But we are lucky. It's still found on the same page in slot 38. Here's slot 38, and indeed. Okay, this is a row whose visibility starts at 48395. So it's the adjacent timestamp interval that is immediately neighboring the old timestamp interval of the old version of the row. Okay, this is also the last version in the chain of rows. As you can see, I'm living on page 9 in line pointer 38, and I'm pointing to myself. This is the loop in the chain that ends the chain by definition in PostgresQL. So this is the newest version of the row. This is indeed an updated version. It's not the original row, it's an updated version. Recall that this is the updated row marker. So this is indeed an updated row, but it itself has not been updated. Okay, so this will change once we perform another update on the same row. And what about visibility? So to see that, let's check our current transaction ID again. It's 48396 in the meantime, and that means that when we are looking at the ternary table, we will see this version of the row because our timestamp is above the xmin and below the infinite xmax value, and we will not see this version of the row because our timestamp lies beyond the upper range of this timestamp interval. This row will be invisible to us in the old version, and we've seen that. We have seen that that row, the old version, is not listed here. It's invisible to us. What we are seeing is the new version. Makes sense. Okay. So as we have just seen, there might be situations where such an update might not find a place for the new version of the row on the same page. So we have been lucky. Everything happened on page 9. Loading page 9 has been the correct page to load. But in general, it will be different. In general, the old row ID of a row might be this, and the new row ID might be this, the following in the sequence, in the chain, and the pages might actually be different. The pages might be different. Okay, so traversing such long update chains might really, in bad cases, lead to very costly page to page navigation, or as I call it, page hopping here. So we would enter the chain at the very first entry because this is the original row ID of the row that has been recorded someplace else. We will see, for example, that in index structures, in these map structures that guide us through the contents of large tables, we will record the row ID of rows that we want to find quickly. And if that index structure has still the old row, the head of the chain, the first entry in the chain recorded, then we would be guided to this old version, only to find that we have to traverse a long update chain, perform some IO costly page hopping to finally find the correct version of the chain that corresponds to our current timestamp. If we inspect all the active timestamps in the system, so there's a number of active users and applications in the system, all of these have assigned timestamps. If all of these timestamps have been advanced so far that particular row versions currently held on the heap file pages will not be visible to any of these applications or users, then it's time to really remove these versions of the row, and that's the process of the vacuum process. That's the task of the vacuum process. So remove old row versions that will never be seen by anyone anyway. Okay. Another effect of the vacuum operation is that structures, index structures, for example, that point from outside to a particular row version, that we will update the row IDs that are recorded in these structures to point to the most recent version. So we will avoid the page hopping, the chain page hopping that can be so IO costly. All right. PostgresQL has some optimizations of this process. For example, the good-natured case. This is exactly the case that we have seen in our example here, that we are guided to another version of the row, but that version is on the same page, is living on the same page. This is the good case, and PostgreSQL has some optimizations internally that that account for this good case, that we don't have to do page hopping. All right, these are updates that are also optimized when it comes to the maintenance of indexes that point to rows from the outside. Updating such index structures maybe is not as pressing and not as vital if the new versions of a row live on the same page. We will not suffer from page hopping. We might suffer from page internal pointer chasing, but not inter-page hopping, which is of course the I/O costly and in the bad case. In these good-natured cases, we can maybe postpone the update of index structures until a later time, because we will not suffer from costly inter-page hopping. So these are the heap-only tuple updates. So updates are really only affecting the heap files and are not being carried out on other structures, on index structures too, for example. So this is the explanation for the hot modifier that we were seeing here in the header of this table. So all of the updates that we've seen here, we have only seen one update. This has been a good-natured heap-only tuple update, a hot update that does not have to lead to an update of an associated index with the ternary table. But updates and on indexes and index structures themselves will be the topic of further discussion in upcoming videos. But not in this video. This is about it, about how updates are being reflected on heap file pages, how different row versions can live together, and how timestamping makes sure that each user sees the correct version of the rows only. All right. Thanks for your interest, and maybe you stay tuned for how all of this works inside MongoDB. It looks quite a bit different there. Okay, see you then.